Hi, my name is Maaz, an aerospace engineer who is passionate about AI, embedded systems, and self-driving cars. I'm excited today to talk with you about MinMax Algorithm. So, let's get started.
MinMax algorithm is one of the most well-known decision algorithms, not only in artificial intelligence, but also in decision theory, game theory, statistics, and even in philosophy. It helps the agent to reach the best scenario or minimizing the loss. It allows the player to find the optimal move, assuming that your opponent also plays optimally. In two players game, MinMax algorithm tries to maximizing the score of each player and minimizing the score of the opponent player. Let's take tic-tac-toe as an example. Tic-tac-toe is a two-player game, X and O. Each player takes a turn, and the player who succeeded in placing 3 of their marks in horizontal, vertical, or diagonal row wins the game. Let's see how can we apply MinMax algorithm on this game. Assuming our player is X and the opponent is O, at the beginning of the game the board is empty, and we can play in any position of the available 9 positions in the 3x3 grid. Let's take the first branch and see where it will lead us. By playing X in the most left corner, our opponent will have only 8 moves to play. And if we take the first branch again and start to dig deeper, that's called depth first search, which is used by MinMax algorithm. Depth first search is a traversing algorithm, which starts from the root of searching tree and traverses down to the most left branch till it reaches all the branch leaves and then move on to the next branch. If we take this state as an example and assume that our agent is X in red, our agent has 3 possible moves as shown in the first level, and there are 2 possible moves for every state in the first level. We continue to expand the board tree until we reach the termination states. We assume that when our agent wins, there will be a positive 1 value, and if our opponent wins, there will be a negative value for the state. And if the game is a draw, then the state will have a 0 value, and this is a termination state. As we mentioned before, MinMax algorithm tries to maximizing values of the states where our player moves and minimizing values of the states where our opponent plays. So there will be maximum levels of our agent moves and minimum levels of our opponent moves. Level 2 is a maximum level. Level 1 is a minimum level, and level 0, which is the root state, is a maximum level. Now let's apply MinMax algorithm on the following example. We propagate till we find a termination state, then backtrace to find the maximum value of the root state. At the most left branch, there is only 1 child for the state in level 2, which is a maximum level. So its value will be 0. Similarly to the next state, it has only 1 child with a value of positive 1. So its value will be a positive 1 too. If we backtrace to their parent in level 1, which is a minimum level, we will take the minimum value, which is 0. As we proceed to the middle branch, the right state in level 2, which is a maximum level, has only 1 child with value of positive 1. So its value is also a positive 1. If we backtrace to their parents in level 1, which is a minimum level, we will take the minimum value of positive and negative 1, which is negative 1. Finally, we will go to the most right branch. Similarly, the right child has only 1 child of a value of 0. And at the end, their parent will have a value of negative 1, which is a minimum of negative 1 and 0. The root in level 0, which is a maximum level, will have a value of 0, which is a maximum of 0, negative 1, and negative 1. So the best move will be to the highest value, which is 0, the most left branch. Time to give a look on the pseudocode. The pseudocode, which is mentioned in IEMA book, consists of 3 parts, 1 function and 2 helpers. First of all, the main function, which is called MinMax decision function. It takes the current state of the port as an input and returns the best possible move for our agent. For every possible action, a new state is formed and the first minimum level is generated. We should find the minimum value for each state in the minimum level. That's where the helper function min_value takes place. Function min_value assumes that each state in the minimum level has a value of positive infinity initially. The function finds the minimum value of a minimum level state by taking the minimum value of its children. If we proceed and expand our tree for one more level, a new maximum level is generated. To find the maximum values for the maximum level states, we use the max value function, which assumes that each state in the maximum level has a value of negative infinity initially, and searching for the maximum value of its children. The two helper functions continue to call each other recursively until one of the two termination conditions appear. Either the player has no possible moves, that will be a draw, or one of the players has won. If we apply the pseudocode in the previous example, we will start with the root state and propagate by calling the helpers many-value and max-value functions, each other until a termination state exists. We will define the maximum levels where our agent plays and where the function max-value will be used, and minimum levels where our opponent will move and the function max-value will be called. At the most left branch, the max-value function will return 0 as there is a termination state. Similarly, the max-value function will return a value of positive 1 as it faces a termination state. The many-value function will return a value of 0, which is a minimum of 0 and positive 1 to this state. Moving to the middle branch, max-value function will return a positive 1 to the right state. The many-value function will return negative 1, which is a minimum of negative and positive 1, to the parent state. Finally, the most right branch. Max-value function will return 0 to the right state. The minimum value function will return negative 1, which is a minimum of negative 1 and 0. At the end, we select the action which gives the largest value, which is 0. So we will go to the most left branch. Now it's time to talk about the algorithm performance. First of all, is it a complete algorithm? And the answer is yes, it is. It can find a solution if there's a solution, and the tree is finite. The second question, is it optimal? And the answer is also yes. It finds the optimal move against the optimal opponent. What about its time complexity? It has a big O of p power m, where p is the number of legal moves at each point, and m is the maximum depth of the tree. The last question is what's its space complexity? It has a big O of p times m, the space complexity of depth first search, where p is the number of legal moves at each point, and m is the maximum depth of the tree. After you know almost everything about MinMax Algorithm, it's time to get hands-on experience. Here's a similar example to solve using MinMax Algorithm. Here is the answer. I encourage you to implement the MinMax pseudocode using any programming language to get the sense of it. Thank you for listening, and I hope you enjoyed. Good luck.